Today we are going to start Chapter 6. To begin with, Chapter 6 in a way kind of ties into where we left off with Chapter 5. In Chapter 5 we were looking at probabilities of random events. We talked about different ways that we can combine them and different types of probabilities that we could find. One thing that we did talk a lot about that is if we do enough experiments, right, and we repeat things over and over enough, patterns begin to emerge. Right? That's what differentiates our empirical probability from a single experiment to our theoretical probability of looking at a bunch of experience over a period of time. In this section, we're going to look at something that is related to probability, but it's going to be a new tool that we're going to use. Right? So to begin with, our first definition for today is a probability model. Right? So a probability model is a description of how a statistician thinks data are produced. Right? By using the word model, it's not an exact science here. Right? So it's not necessarily going to fit our real life 100%, but we hope that it's a pretty good idea of what we're looking at. As we're looking at this, we can tell if a model is a good model by noting whether the probabilities that it predicts are matched by real life outcomes. We're going to use these probability models to talk about our next thing, which are probability distributions. Right? So probability distribution is represented in different ways based on the types of variables and the types of outcomes that we have. So we could have discrete outcomes or continuous outcomes. Both of these types of outcomes are numerical or quantitative variables. Right? So we're not thinking qualities, we're thinking numbers. Now the big difference is what types of numbers we have. Right? So our discrete outcomes, right, or our discrete variables are numerical values that we can list or count. So the big thing when we're thinking about discrete variables, we can only use whole numbers. Right? Continuous outcomes or continuous variables, they cannot be listed because they occur over a range. Right? So when we're thinking about continuous outcomes, we generally use rational numbers. We could use fractions or decimals. So the big thing is here as we're looking at continuous outcomes, these are generally things that can be measured. So discrete variables are ones that we can list or count, and continuous variables are ones that generally we think about as something as being measured. And so that's the big difference between those two. In our first example for this section then, we're going to simply decide if a list of different types of variables are discrete or continuous. Okay. So identify each of these numerical variables as discrete or continuous. The weight of a sandwich you are served at a deli. Since weight is something that is measured, right, this is going to be an example that is continuous. Weight is something that is measured. Right? We could have some sort of decimal values or fractional values if we were thinking about the amounts. You know, the sandwich could be 6.5 ounces, right, or something along those lines. The number of people in the next passing car. Right? In this case, the number of people is something that we would count. So since this is something that we would count, this would be an example of a discrete variable. Right? So it's something that could be listed or counted. For C, the number of contacts stored on the phone of a classmate. Again, we're looking at a number of things here. This is another example of a discrete variable. It could also be counted. The elapsed time between leaving the house and getting to school. In this case, the elapsed time is going to be a continuous variable. Again, it is something that can be measured. It could include fractions or decimals. Right? We might not go as far as minutes. We could do minutes and seconds. We could do parts of seconds and something along those lines. So our elapsed time would be something that would be measured. So that would be another example of a continuous variable. All right. Based on the type of variable that we're looking at, where our probability distributions are going to be different. Right? So again, we're thinking that these are all models of real life things. And then from these models, we take that information and based on the type of variable that we have, we're going to have two different types of distributions. So the first type of distribution that we're going to focus on is our discrete probability distribution. So a discrete probability distribution is one that shows the probability of each possible outcome when all the outcomes are discrete variables. Right? When we're thinking about these, again, discrete variables are something that can be counted or listed. So discrete probability distributions are pretty easily shown as either tables or graphs or sometimes even equations. So we'll see some examples of each of these. So looking at this one down at the bottom, right, we have both of these images show information about the same thing. So it shows a probability distribution for the number of stars given as a rating to a particular book on Amazon by a randomly selected customer. Right? So this particular book, right, the probability of it having a 5-star review is 0.62. The probability of having a 4-star review is 0.23. The probability of having a 3-star review, 0.10, 2-star, 0.03, 1-star, 0.02. Right? So we have a limited number of things that we have here. Right? We can count the number of stars that it has. Does it have 1, 2, 3, 4, or 5? Then based on those probabilities that we have, notice that the visual image right next to it shows vertical lines corresponding to each of our different probabilities. So a 1-star had a 2% or 0.02 probability. Then as we go across, as we work up our table, we see all of our different probabilities represented by vertical bars going to the height of the probability that we see listed in that other column. This is similar to what we talked about back in chapter 2 if you think about when we were doing our relative frequency histograms. Right? The difference is instead of drawing this as a histogram, we've drawn this just as a simple graph with a vertical line for each different possible outcome that we have. Another way we can visualize a discrete probability distribution, we do see a graph here as well, but instead of a table, notice that we have a formula, 1/2 to the x power. Right? This is related to the probability of distribution of flipping a coin and every toss being landing heads up. Because if we think about this, using our probability information from chapter 5 that we used, right? Our probability of selecting exactly 1 heads. Right? We toss a coin, we have a 1 out of 2 chance of flipping 1 heads. Right? If we toss 2 coins, right? Well, we have a 1 out of 2 chance for each. Right? So our probability of 2 is 1 out of 2 times 1 out of 2. Right? Our probability of 3, right? We would do 1 out of 2 times 1 out of 2 times 1 out of 2. Right? So using a multiplication rule from the previous section, right, if we're thinking about how many heads, right, we would simply be multiplying the probability of 1 out of 2 times itself that many times. Right? That's what exponents show. Right? So notice this first one is equal to 1/2 to the first power. Right? This one is equal to 1/2 to the second power, right, which is 1/4. 1 times 1 is 1 squared, 2 times 2 is 2 squared. Right? This next one is 1/2 to the third power, right? Or 1/8. So in this case, our probability distribution, instead of presenting it as a table, it's presented as a formula. But then notice that our graph that's next to this, right, does show this following information. Right? The probability of flipping 1 heads is 1 out of 2. That's that first bar, right, 50%, 0.5. Right? For 2, 1 out of 2 times 1 out of 2, well, that's 1 out of 4, which is 0.25 or 25%. That's where that second vertical line goes to. And then as we progressively flip more coins, right, our fractions are going to keep getting smaller and smaller, and all of those bars are represented appropriately. All right, so now that we've looked at a couple of examples of both a table and an equation and seen a graph that shows a discrete probability distribution, we're going to work through drawing one out ourselves in this next example. Okay. So we're going to roll a fair 6-sided die. As we're rolling this die, we're going to win $4 if we roll a 5 or a 6. We're going to lose $5 if we roll a 1. And for any other outcome, you will win or lose nothing. So our probability of winning $4, right, that means that we have rolled a 5 or a 6. Right? That is 2 outcomes out of the 6 sides of our die, right, which is 1 out of 3. We're going to go ahead and change that to a decimal. We're going to round it to 3 places, so we're going to have 0.033. Our probability of losing $5, that's what happens if we roll a 1. Right? There's exactly one number 1 on our dice. So 1 out of 6, again, if we change that to a decimal, we get 0.167. Right? The probability of winning or losing nothing, well, we've already used the numbers 5, 6, and 1. So we have 3 numbers that are left over. Right? So 3 out of 6, it gives us 1/2, which is 0.5. Right? So if we wanted to list out, again, probability of winning $4 came from rolling a 5 or a 6. Right? Probability of losing $5 came from rolling a 1. And our probability of winning or losing nothing were our other 3 numbers. Right? If we rolled a 2, 3, or a 4. All right, now we're going to take this information, we're going to put these probabilities in our table. Right, so losing $5, if we look at this second line here, losing $5 is 0.167. Winning or losing nothing, well, that's our 50-50 shot of 0.5. And winning $4, that reduced to 1 out of 3, or 0.333. Now we're going to take this information and we're going to draw lines, vertical lines on our graph to represent this. All right, so losing $5, we had a 0.167 probability, or about 17%. So if we look at this probability distribution graph on the bottom, right, our horizontal axis has to do with the amount of money, right, that's either being won or lost, and our vertical axis has to do with our probability. So losing $5 is going to be represented by this -5 here, and our probability is 0.167. So we're going to take and we're going to draw a vertical line that goes up to about 0.167. The next possible outcome, winning $0. Winning $0, we have a 0.5 or 50% chance. So we're going to draw a vertical line here going all the way up to 0.5. Right? Our last possibility of winning $4, about a 33% chance, or 0.33. So we're going to draw a vertical line here that goes up to 0.33. Just to make it look nice and finished, we put the little dots up at the top rather than just leaving them as plain vertical lines. And in this case, we're done. Right? We don't have any other values or any other different possibilities. So we don't need a bar at every single number. We just need bars, vertical bars, at the places where we have actual different outcomes for this particular probability distribution. So again, we're looking at a discrete probability distribution because we could count how many times each of our different events happened. Right? Once we counted those, we found our probabilities and thought of those as decimals, and then we graphed them into this table, so we have a graph of this discrete probability distribution. That's about all that we're going to do with probability distributions for discrete variables for this chapter. So this last example for section 6.1 that we're going to talk about, and really the rest of the chapter, we're going to focus on continuous probability distributions. So continuous probability distributions, remember, are something that can be measured. So the difference is here, we don't have a specific set of outcomes. Right? So we have a bunch of different possibilities depending on fractions, decimals, things like that. Right? It's not as cut and dry as far as thinking about discrete probability distributions. So instead of representing these as bars with vertical lines, what we're going to do when we're looking at continuous probability distributions is we're going to think about these probabilities as being areas under some sort of curve. So continuous probability distributions are represented as area under curve. The curve itself is called a probability density curve. As far as the different shapes go, right, our curves could look like a lot of different things. Right? So we have here something that is kind of rounded. In this particular one, this image shows the probability distribution of times waiting in line at a particular coffee shop. The highlighted area represents the probability that the time is between 0 and 2 minutes. Right? So as we're doing these and as we're thinking about these, our curves could look different. The one thing that is always true for all of these is the total area under the curve is equal to 1. Right? It's equal to 1 because we're thinking about the area as being 100%. Right? If we were to look at those tables that we saw in the previous one and add up all of our probabilities, in both cases, right, they would add up to 1 or 100%. The same thing is true here. The area under our curve is equal to 1. Now, the only downside is finding area under curves is very difficult. Right? So looking at this example, if we want to figure out exactly this area and exactly this percentage, right, it's very, very difficult to do without technology. Right? So as we proceed through the rest of the chapter, we're going to see one example at the bottom where we're dealing with a rectangle, because finding areas of rectangles is relatively easy. And then we're going to focus on normal curves for the rest of the chapter. But this is something that we could do for any type of shape or curve, even if it's not a nice symmetric distribution like we're going to see in the next section. All right. So for this last example for this chapter, or excuse me, for this section, we are going to look at waiting for a bus. A bus arrives every 12 minutes. Find the probability that a person arrives at a bus stop at a random time will have to wait between 4 and 10 minutes for the bus. So since it arrives, and we're looking at this, and we're focusing on our 4 minutes to 10 minutes, right? This rectangle down at the bottom represents a bus that shows up every 12 minutes. Right? We're focusing on the shaded area down here between 4 minutes and 10 minutes. And so this is a continuous probability distribution because it could be anything between 4 and 10, and it could be down to a fraction of a second. So it is a continuous variable. And we want to find the area under, in this case, again, we don't necessarily have a curve, we have a nice rectangle to deal with. All right, so our base. Well, our base, we're thinking about this 4 to 10. And if we think about our distance from 4 to 10, well, if we were to do our subtraction, right, 10 minus 4 gives us 6. So we have a 6-minute window that we are looking at here. We are told in our graph that our height is 0.08333. So our height is 0.08333. Right? Again, and then we should remember that area of a rectangle is base times height. So we're going to take this 6 time this 0.08333, and it works out to be 0.4998. And if we look at that, that's really close to 50%. So we're going to finish this off by saying the probability a person waits between 4 and 10 minutes is about 50%. Alright, so as we finish this section up, as you're working through the homework, you should be focusing on the difference between discrete variables and continuous variables. And then you'll be asked a couple of questions about discrete probability distributions and kind of some simple continuous probability distributions such as this last one. And then in the next section, over the next couple of days, we're going to focus more on our continuous distributions of a certain type.